So now we can have a look at the last two letters of Dr. Cape Town, and that is P for parallel lines and T for tangents. So with parallel lines, we know that we can have co-interior, corresponding and alternate angles. Now when we have corresponding angles, what we look for is an F shape. And when we do have that F shape with our parallel lines, we know that those two angles indicated there are corresponding, and as a result they are going to be equal. Then we also have alternate angles, and when we do have alternate angles, we're looking for that Z shape. And again, alternate angles are going to be equal. And then if we have co-interior angles, we're looking for the C shape, and then co-interior angles are not equal, but they are supplementary. They do add up to 180 degrees. And note, when you do claim some sort of properties of these angles using the parallel lines, you need to just indicate which lines it is that are parallel. Then, in this instance here, we are not told that we do have parallel lines, but we are told information about the angles. So if you have corresponding angles that are equal, then we can claim that the lines are going to be parallel. If you have alternate angles that are equal, then you can also claim that the lines are parallel. And if you have co-interior angles that are supplementary, then you can also claim again that the lines are parallel. So if you are given parallel lines, you can make inferences about the angles, and if you are given angles, you can then make inferences about the lines and decide whether they are indeed parallel or not. Then we're going to look at tangents. The tangent to the circle is perpendicular to the radius or the diameter of the circle at the point of contact. So if you've got a radius and it meets a tangent, they meet each other perpendicularly. In other words, there's a 90-degree angle there. And same goes for a diameter. If a diameter meets a tangent, then that is going to be a perpendicular line. So those are going to be 90-degree angles. And the reason is quite simple: tan perpendicular to radius or tan perpendicular to chord. Then, if a line is drawn perpendicular to a radius or a diameter at the point where the radius or the diameter meets the circle, then the line is a tangent to the circle. So in the previous one, we said we've got a radius, we've got a tangent, as a result we've got a 90-degree angle. Now we're saying we've got a radius, we've got a 90-degree angle, so that line AB there has to be a tangent. And then the same goes for a diameter and some line that are perpendicular to each other at the circle. That is also going to give us a tangent. So CD there is a tangent as well, and the reason is line perpendicular to radius. Next up, we've got the tan-chord theorem, and for this particular theorem, it's very important that you understand your circle terminology so that you can understand the theorem statement. So it says here, the angle between the tangent to a circle and the chord. So if we identify there the tangent and the chord, then the angle that we are talking about is indicated as such. Now it's drawn from the point of contact, and it's equal to the angle in the alternate segment. Now the alternate segment has to be on the other side of the chord, not on the same side as the angle that we've indicated, and the angle that is subtended by that chord, well, that's the one that it's equal to. So that angle there is being subtended by that chord, and so we can claim that those two angles are then the equal angles. Now note that when we do have this tan-chord theorem, we can also apply it to the other chord and the other side of the tangent, and so those green angles there are also going to be equal to each other. And the reason is going to be the tan-chord theorem. Then, if the line is drawn through the endpoint of a chord, making with the chord an angle equal to an angle in the alternate segment, then the line is a tangent to the circle. Now here the theorem statement is quite dense, but basically it's just saying if you've got those two angles that are equal to each other, that we usually claim are equal because of the tan chord theorem, then we can go and say, this AB thing, that's got to be a tangent. So tan chord, we're going to go and say that because we have a tangent, these two angles are equal. And then if we have the converse of the tan chord theorem, we're going to say, well, these two angles are equal, so as a result, this AB thing here, that's got to be a tangent. Now, note the following common pitfall that you may well fall into. And that is that in this particular instance here, if you try to apply the tan chord theorem, then you might say that x is equal to y, but x is not equal to y. So you've got to be careful. The 3 points that we use when we apply the tan chord theorem, they have to be concyclic in order for us to be able to apply it. And remember, concyclic is a word that means together on the same circle. So there, the 2 pick points, that's on the circle, that's great, we've got a chord, but the green point there is not on the edge of the circle, and so we cannot go and claim that x is equal to y. Continuing on from there, when 2 tangents are drawn to a circle from the same point outside the circle, they are going to be equal in length. So B there is the point outside the circle from which the 2 tangents are drawn, and thus AB will be equal to BC. And the reason there is tangents from a common point. Now note the following pattern that recently or frequently appears. When you do have these tangents from a common point, and you also have radii that meet those tangents, then you often form a kite and you form right-angled triangles. Now recall from not too long ago that AB must be equal to BC because they're tangents from a point, common point, and that because this 2 lines are radii, they also have to be equal in length. And then we know that radii meet tangents at 90 degrees, and so we can claim that this figure here is a kite, because we do have 2 pairs of adjacent sides that are equal in length. Then, if we draw a line from the center to that common point, we can see that it actually divides this kite into 2 right-angled triangles. And do remember that when you have right-angled triangles, Pythagoras' theorem is one of the tools that you have in your toolbox that you can use. So, let's see how we can apply all of these things. So in the following, we've got A, that's the center of a large circle. C is the center of the small circle. AB is the diameter of that small circle. DF is a tangent at F, and DB is a tangent to both circles at B. And we are told that BFD is equal to X. So first, we have to prove that FG is equal to GB. Then we have to find 3 other angles that are equal to x, and then we have to find ABG in terms of x. So it might not be a surprise to you at this point, but I'm going to start by applying Dr. Cape Town. So first I'm going to look for a diameter, and I know that AB is a diameter. And as a result, I know that AGB is a 90-degree angle because a diameter subtends a 90-degree angle. There are no other diameters, so then I will look for radii or angles, lines from the center. So if we look there at A, we can see that AG is a line from the center of the large circle. We can also see that that line from the center is in fact perpendicular to FB. And when you have a line from the center that is perpendicular to a chord, then you know that it bisects that chord. And as a result, we can claim that FG is equal to GB, and that is what we needed to indicate for the first question. Then, if we use the fact that we have tangents from a common point, then we can also claim that FD is equal to DB. Now, why have I skipped all the way ahead to tangents? Well, there weren't any other radii, so AC and CB are radii, but that's not super interesting that they're equal to each other. We do have the centers of the circles, but we don't have angles at the center that is subtended also by the same chord that at the circumference. We don't have chords that are equal, we don't have parallel lines, and so we can skip ahead and work on the tangents. So tangents from a common point, we know FD is equal to BD, and then that means we've got an isosceles triangle. And for an isosceles triangle, the angles opposite the equal sides are equal. So that then means that because that DFB is equal to X, FBD must also be equal to X. Then, if we use the tan chord theorem in the small circle, we can see that DBG, the angle X, is an angle between the tangent and the chord, and then in that small circle, that same chord GB subtends the angle GAB. And then so, we can conclude that GBD and GAB are equal, and we can call both of them X. Then we can see that AGB, the triangle, the right angle triangle, is a triangle in which we have two of the angles. And when we have two of the angles, we can always find the third angle by taking 180 and subtracting those two angles, and as such we will find that ABG is then equal to 90 minus X. Then, if we look at the large circle, we notice that DB is also a tangent to the large circle at B. So the angle X between DBF is an angle between the tangent and the chord, and then the chord BF subtends the angle BEF. And so we then know that BEF must also be equal to X. And if we look at FBD, we have a triangle, we've got two angles, and then to find the third angle, we simply go 180 minus the X, that gives us 180 minus 2X. So, have we found three other angles that are equal to X? Absolutely we have. Did we find ABG in terms of X? Absolutely we have. We found it to be 90 minus X.